Okay, hello everyone. My name is Maxwell Buss, and today I would like to talk to you about Majorana pi modes in driven two-dimensional magnet superconductor hybrid systems. Um, as you see here, I am a PhD student at the University of Illinois at Chicago, and this talk was originally given at the APS March meeting 2022. I am making this video to upload to the online platform for the meeting. Okay, so before I get started with the talk in earnest, I would like to acknowledge my collaborators on this project, my advisor, Professor Dirk Moore, as well as my colleague, Yasmin Bito, both, of course, at UIC. I would also like to acknowledge funding from the United States Department of Energy. And let's start off by discussing why these magnet superconducting hybrid structures are actually interesting. And the first point is that they can be manufactured, in fact, have been manufactured by this group among others. Here you see a topographical map of an iron monolayer deposited on top of a rhenium surface. And if one looks at a plot of dIdV for this system, one sees strong evidence of Majorana edge modes at the edges of this iron monolayer. Additionally, it has been shown, for example, in this paper, that topological phases can be quantum engineered using complex magnetic structures. For instance, here, one sees a skyrmion lattice, and it turns out that by tuning the radius of these skyrmions, one can actually move between different topological phases, as is demonstrated through the topological phase diagram here, which tracks the Chern number for various parameter sets. On the other hand, recent experimental advances have actually made it possible to dynamically control such magnetic structures, either by tuning the exchange coupling of individual adatoms directly, like you see here, or by changing the relative spatial orientation of magnetic impurities, for example, through the twisting of an impurity dimer, as one sees here. Additionally, it has been shown that the periodic driving of one-dimensional topological superconductors leads to the emergence of finite energy Majorana pi modes, and we wanted to see naturally if this could be extended to two-dimensional magnet superconducting hybrid structures. So how do we actually go about modeling such systems? Well, of course, we begin with the static part of the Hamiltonian that you see here. We have a hopping term, which considers only nearest neighbor interactions. We have an on-site chemical potential term. We have a S-wave superconducting term. And we have a Rashba spin-orbit coupling term here. Now, rather than having the magnetic structure simply be static, we allow it to be time-dependent. And in fact, we will drive it periodically. And because this driving is periodic, we can actually compute the Green's function of such systems using the Floquet formalism. And from there, we can simply extract the spectral weight function through the standard approach seen here. And the reason that we do this is that Majorana zero modes, or Majorana edge modes, are known to appear localized at domain walls in real space, and we want to see whether or not these finite energy Majorana pi modes occur, first of all, at all, and if they do occur, whether they occur localized at a time domain wall or whether they are delocalized instead. Right? Okay, so let's begin by driving a two-dimensional magnet superconducting hybrid system. We'll start with a system that's topological for the static case, and we'll let our system be translationally invariant. This is what we see in the case of static magnetic structure. Now, if we drive the magnetic structure, like so, we actually see that when the driving frequency is energetically equivalent to the superconducting order parameter, one sees a closing of the gap at zero energy. If we continue driving the system at higher and higher frequencies, when the driving frequency is equal to double the superconducting order parameter, we actually see the emergence of these finite energy Majorana pi modes at plus or minus half the driving frequency, that is, at the boundaries of the flow K zone, which is, of course, also equivalent to plus or minus the superconducting order parameter. This is also perhaps better visualized in the energy versus driving frequency plane. One sees here the gap closing at zero energy, and these two brighter crossings here correspond to the Majorana pi modes that we see here. Now, in contrast, if one considers a system which is topologically trivial in the case of static magnetic structure, then these pi modes do not occur. And in fact, we can also see that here in the energy versus driving frequency plane through the lack of these bright crossings here. Okay, so now we know that these pi modes can be seen, but we want to know, are they localized near time domain walls, similarly to how Majorana zero modes, as I mentioned before, are localized near space domain walls. So let's take a look at an animation showing the evolution of the spectral weight as a function of time for such a system. Okay, we see as this goes along that the spectral weight function for these Majorana pi modes seems to be relatively constant and undergo only small fluctuations, even when you saw halfway through the sign of the magnetic coupling flip. And indeed, if we look at this in time more directly, we can see that the spectral weight function actually only does indeed exhibit small fluctuations. In time, right here, this orange dashed line corresponds to where the magnetic exchange coupling actually flips signs. Okay, so now that we have seen that time domain walls do induce Majorana pi modes, but that they are delocalized, we want to see what happens to these Majorana pi modes with different types of domain walls in time. Okay, so we're going to try out 3 different types of time domain walls. Number 1 here in orange is a simple sine wave driving of the magnetic structure. If we do that, we see this. And then next in green is the first few non-vanishing harmonics of a square wave. If we drive the system with that, we see this. And after that is an actual exact square wave driving in blue. And if we drive the system's magnetic structure with that, this is what we see. And you'll notice that there is almost no difference, in fact, between the several harmonics approximating a square wave shape and an actual square wave shape. And more generally, what you'll notice is that the sharper these domain walls are in time, the sharper the features of our spectral function, right? For the sine wave, our spectral function is a lot less sharp than it is for instance, the square wave. Okay. So now let's move out of our translationally invariant system and move to a ribbon system, which has domain walls in both space and time. Now, if we drive the magnetic structure of that system, recall for the translation invariant system, we saw this, and these pi modes aren't existing in a gap, but rather surrounded by bulk states. For the ribbon system, these bulk states are actually going to get projected near the pi mode, and while we still do see this pi mode, it is in fact surrounded by these bulk states. And of course, because we are introducing a domain wall in space now, we are also going to see a Majorana 0 mode, but it is localized completely at the edges of the system, which is where I have the domain wall set up. And yeah, clearly if we look at this plot here, we see that the spectral weight of this Majorana 0 mode dies away very quickly in the bulk. By contrast, the Majorana pi mode is entirely delocalized throughout the system's bulk, as we see here. So let's summarize what we've found. We've found that finite energy pi modes do indeed appear under the periodic driving of two-dimensional magnet superconducting hybrid structures. We've also shown that such modes are allowed to coexist with Majorana 0 modes when we have both space and time domain walls present. However, while Majorana 0 modes are entirely localized in space near the domain wall, Majorana pi modes are delocalized, both in space and in time. With that, I would like to thank you for your time, and you can feel free to ask questions on the online platform. Thanks again.